Good afternoon, everyone. Welcome all of you for today's live session on this Power System Engineering Week 3. I am Gagan Meena and I am doing PhD in Electrical Engineering Department at IIT Bombay. So we'll start with today's session. So this will be the agenda for the today's session. First of all, we will go through a brief overview of Week 3 material, and then we will discuss some questions on Week 3 material, and then if you have any doubts, you can ask. In between, also, if you have any doubt, you can ask. So just to remind you, the deadline for assignment 3 is 14th Feb. So try to submit it before 14th Feb. And the links for the recording of these live sessions, as well as the material, the PPT used, presentation used during the sessions, is available on this on the portal in the problem solving session tab. You can go there and you will get a link for Google Drive, where you will find link for links for both recordings of live session as well as the PPT used. So let us start with the overview of week 3. In week 3, first thing was a continuation of the underground cable, and in that thermal resistance of cable was discussed, and then next topic for the 4 lectures was the transient overvoltages. In thermal resistance of underground cable, first of all, insulation of single core cable was discussed. And so it was thermal resistance for single core cable and then multi core cable. So for this, formula was given, which was in, and the formula is similar to what we use for calculating the insulation resistance of the underground cable. So here DGI is given as GL into dx divided by 2 pi x. So considering the cable, where this is in core, then we have insulation, the outer radius. We can have a small strip of delta x length, and over which we can integrate to find out the final. Just a minute. Yes. So to find out the final, we can integrate final resistance. So here GL is the thermal resistivity similar to the electrical resistivity, and it is equals to 5.5 degree centigrade meter for high voltage cables, most of the high voltage cables. So this is used. So to find out the thermal resistance, we will integrate it. Integrate GDI with respect to x from radius to the outer radius, and then you can find out GL upon 2 pi ln R by R. So for insulation resistance, we had, instead of GL, it was rho by 2 pi and ln R by R. Here rho is replaced by the thermal resistivity instead of the electrical resistivity. That is the only difference here. Yes. So this is the thermal resistance per unit length. So this is thermal resistance per meter length, which is GI, and its unit will be thermal ohm per meter. Thermal ohm per meter. And for insulation of multi-core cable, we cannot finding out formula is not that easy. So we have from empirical experiments, from experiments we have the empirical results, so which we there are certain curves, and based upon the curve we can find out the thermal resistance. So here on y-axis it is thermal resistance per unit length, and on x-axis it is the ratio of total dielectric thickness divided by the core diameter. So such graph will be provided even when if questions are there, then such graph may not be provided, but data points will be provided in the form of tables or something, and then you can easily find out the for the corresponding value of total dielectric thickness and core diameter. You can find out the thermal resistance. Then we also have this protective covering, right, which is the bedding and serving. It is in the form. It is also in the form of cylinder. It is also above the cable, protective covering, and that covering also has a thermal resistance, protective covering. So all these thermal resistance is why we are finding out, because we want to calculate the current rating of the cable. An expression which is called, so that was GI, insulation thermal resistance of the insulation. Now this is the thermal resistance of the protective covering, which is GP. So I for insulation, P for protective covering. So GP is also given by similar formula. Instead of GL, we have G2 by 2 pi ln R2 by R1. This is also in thermal ohm per meter. G2 here is the thermal resistivity of the bedding and serving, which is about 5 degrees Celsius meter per watt. Then R1 is the radius over the sheath. So radius over and above the insulation, over the sheath, which is in meter. And R2 is the external radius of the cable. Or here for the insulation it was ln R by R, where R was the internal radius and R was the R plus thickness of the insulation. Okay. Then above this we have this soil, right? We have the soil because the underground cable, the cable is inside the, it's underground. So above protective covering, we have the soil around it. So the soil itself, it also has resistance, which is given by G3, same formula, but ln 2H by R2, where R2 is the external radius and H here is the height below the ground, out from the ground. So the height the depth at which the cable is underground. So if the cable is buried h meter below the surface, then the thermal resistance due to soil is given by this. So these three are the three thermal resistance, one for insulation, protective covering, and then soil. And insulation resistance for armor is neglected. As we saw last time that we have this conductor here, then above the conductor is the insulation, above which is sheath, above it was armor, and above the armor was the protective covering. Because the thickness of armor is very less, so its thermal resistance is also negligible, which is neglected here. That's why we have only three thermal resistances, one for insulation, one for protective covering, and another last one is for the soil. So all these three are required for calculating the current rating of the cable. So for that we need temperature, and just as we apply Ohm's law in electricity, we have Ohm's law, we can have its analogous Ohm's law in for thermal resistance also. For that we need here we use voltage differences. Here instead of voltage we will be having the temperature differences. So if a multi-core cable is there and there are three cores, then and the loss I square R loss in one cable is I square R AC, then in n core cable it will be n I square R AC, right? And this is equals to the temperature difference between conductor and the sheath divided by the thermal resistance of the insulation. Okay. So this will be watt per meter. So this is the conduct. This is the copper loss in the N core cable, which is N into I square R AC, which is theta C minus theta S by GI. And suppose if the copper loss in the sheath is some lambda I times the conductor copper loss, and an armor thermal resistance we have already neglected, so we are considering that the loss in armor, copper losses in armor is also negligible. Then the total losses will become 1 plus lambda I into n I square RAC watts. Okay. And now the protective covering and the soil has to pass these, have to pass the heat generated through because of these losses, these total losses. So these total losses will be lost in the form of, this will be dissipated in the form of heat. This heat losses has to need to be passed on through via the protective covering as well as the soil to the atmosphere. So this is the total. So total loss comes out to be 1 plus lambda I into n into I square R AC, which is equals to So this is theta S minus theta A, where A is the ambient temperature, theta A divided by the thermal resistance of the protective covering as well as the sheath. Sorry, the thermal resistance of the protective covering and the soil. So this is soil and this is the protective covering. And initially what we wrote that I n square RAC is equals to theta. The heat loss in the conductor is to be passed through the sheath. So this is given by theta C minus theta I. So this is theta insulation divided by GI. So this is also theta C minus theta is divided by GI. So this entire loss, if we consider only the conductor loss, then these losses have to pass through the protective covering as well as the soil. So this is theta C minus theta S by GI, and this is theta S minus theta A by GP plus GS. So finally, we get the formula for current as I is equals to theta minus theta A. So theta minus theta A is ambient temperature divided by NRAC into GI plus 1 plus lambda I GP plus GS. And this is what will be the effect of dielectric loss in this? The effect of dielectric loss will be to reduce this current rating. Because above the 66 kV voltage, the dielectric losses are also very significant and they are independent of load current. The current causes an increase in the temperature of dielectric. So as a result of which, this will current rating is limited by the dielectric loss. Then we also saw after this current rating what is the charging current for a cable. The charging current for a cable is given by V by XC, which is V by omega C, and this V will be phase voltage, so it is V by root 3 omega C. So this is 1 by omega C, so it will be omega C V by root 3, which is 2 pi FC V by root 3, right? So three phase reactive power will be root 3 into Vc, the charging current into V, and this will be root 3 V into 2 pi FC V by root 3. So what it will be? It will be to C also we can substitute C as 2 pi epsilon naught epsilon r upon ln r by r. This if we substitute here, then we'll get 4 pi square f v square epsilon naught epsilon r divided by ln r by r. It is VAR per meter. And this flow of charging current causes heating in cable, and therefore the load current capability of cable is decreased. And after this, after discussing this, we entered into what happens is what is the transient overvoltage. So there are overvoltage due to switching. And the interruption of capacitance current give rise to these overvoltages. There is also current effect. If a significant portion of a transmission distribution system is underground cable, then there is a rise in voltage of the load point, especially during the no load or lightly load condition. And at that time, the voltage at the load end or the receiving end, this is sending end and this is the receiving end, and if the load is very light or there is even no load, and this voltage VR becomes very high, may become more than Vs. So to avoid the situation, what we do, we need to absorb these capacitive wires. So a shunt reactor is used to absorb these reactive wires. And then we discuss the HVDC cables. What is the benefit of using HVDC cable and how they are different from the AC cables? What happens? What are the difference? So they are used for the direct current transmission, and their advantage is that they have no charging current. DCA, so they have no LNC components, only I square R loss is there because only resistance is there. No alternating current here. And electric stress distribution here, charging current is present. Here even reactive losses is there. Reactive power loss is also there. Then here we saw that the electric field distribution was like this. If this is the conductor and this is the sheath, then the electric field distribution was like this. Maximum at the surface of the conductor and then it gradually reduces towards the sheath. It was maximum at the surface of the conductor. However, here in HVDC, it is the electric charge distribution. Here it is given by the dielectric capacitance in AC cables. But in DC, it is determined by the resistance of the dielectric. These are main major difference. And this resistance of dielectric appreciably decreases with increase in temperature. And you can see the resistance of dielectric at the 60-degree NV is almost 1% of the resistance at 20 degrees Celsius. So resistance decreases so significantly. Therefore, thermal consideration influence a lot. The electric stress distribution is in dielectric is significantly influenced by the temperature in HVDC cables. Here I was saying that the electric distribution decreases from the conductor to the sheath in AC cables, while in DC cables the electric stress increases. This is called as the stress inversion phenomenon. So here the stress will be like this more. That it is minimum at conductor surface and it increases to the sheath and can be large at sheath. And this can lead to troubles at terminals and joints where the longitudinal stresses are created. So, and because of this, the DC cables have very high current and voltage ratings. They can have a lesser insulation thickness and are compact. And DC cables are always single core and stranded. So they may have plastic or impregnated paper insulation, oil and gas filled DC cables. And they have been used for more than around 100 kilometers. So after discussing this HVDC and HP, comparing this HVDC cables with the AC cables, The over voltages was discussed, transient over voltages, and next part in the next week will be the insulation coordination will also be discussed. The transient phenomena is always a aperiodic phenomena which appears only for a few very short duration. An example for such transient phenomena are the voltage or current surges. And voltage surge can be introduced by a sudden change in voltage at any point in the power system, and its velocity will depend upon the medium in which the surge is traveling. And such voltage surge is always associated with the current surge also. And this so what's the difference? This voltage surge will lead to current surge, and these are due to because of the charging or discharging capacitive current, which are introduced by change in voltage across the shunt capacitance. So if we consider a lossless transmission line, and it is something like this, it is made up of several segments of LNC. LNC is like here is the source. If the surge is traveling like this, then if because it's very high frequency, omega it will almost it is open. And so surge voltage are created by currents which are due to charging discharging current. So if you change in voltage across one capacitance, and the surge voltage can be created because of lightning strike, which is the most common, then because of switching or faults. Yeah, so when so we the study of this transient problems are made by using this long transmission line model. Here if you have an V and here if we have a switch, we have L and C. Here L and C. Then what will happen when the switch S is closed? First the capacitor will charge immediately to its instantaneous applied voltage. However, because the first series inductor, since it acts as an open circuit, because the frequency of surge is very high, as a result, omega is very high, so this impedance is very high. It's like open circuit. The second capacitor, I think I made a mistake here. We have this capacitor here and then inductor here. Because the frequency is very high, this is open. This is charged immediately. And because this is open, the second capacitor does not immediately respond, but it responds with a delay. So you can see it will happen like this. The voltage from here will go here. So it is traveling like this from this left to right with certain delay. So from the sending end to the receiving end, there is a gradual buildup of voltage over transmission line conductor. So it is as if the voltage wave is traveling from this sending end to receiving end. And that is why we saw that we have this traveling wave equation for transmission line, which are the d square v by dx square is equals to 1 by v square d square v by dt square, and then dou square I by dou x square is equals to dou square I by dou t square. V is 1 by 2 centimeter per second. And the solution of it comes out to be in the form of forward. It's a composition or superposition of two things. First is a forward wave and another is the reverse or a backward wave, backward voltage and current. And so finally we get this, we see that the voltage and current which are traveling on this transmission line are like traveling waves and they are composed of two components. One is forward moving, one is the backward moving. And the voltage and current at any point of this transmission line will be a sum of these two components, forward and reverse, or the backward voltages, forward moving or the backward moving voltage. So it is like V is will be V forward plus V backward as well as I is equals to I forward plus I backward, where we can see V forward is equals to ZC, the characteristic impedance, into I forward, and V backward is equals to the current is moving back. Voltage is so if voltage is VB is like this, then current will be like this in the opposite direction. If VB is like this, then the current will be like this. IB. VB is opposite to IB also. ZC we know it is under root L by C. I forward you can write from here VF by ZC and here V minus VB by ZC. So I will be so then next we saw the surge power input and the energy storage. The surge power input will be P into I in watts. Here we have electrostatic component. The surge power to the input is like this. Since the receiving end is open circuit and the line is assumed to be lossless, energy input per second is equals to the energy stored per second. And it has so energy stored in turn is equals to sum of the energy stored is equal to sum of the two components, which is electrostatic and electromagnetic. So electrostatic component is half CV square and electromagnetic component is half Li square. So this is for a lossless line. And where receiving end voltage is zero or it is open circuit. So total energy stored is Ws plus Wm, which is also equals to since the two components of energy storage are equal because what is happening this is C and this is L. If this is charged and it is stored here, then this will release it and it will be charged. So whatever is being stored, it is being released. So this that's how it is propagating forward in the forward direction. So these two are components are equal. So half CV square is equals to half Li square and P is equals to V into I. P is equals to W into V velocity. So if it is half I square divided by root LC, so it comes out to be I square ZC. Okay. So power is we can write it as P is I square ZC, which is also equals to V square by ZC. Okay. So for a given voltage level, surge power resistance is this power is V square by Z C dependent on the voltage. If voltage level is same, then it is indirectly proportional to the characteristic impedance. And we know that the surge impedance for the cables is higher. The surge impedance, the surge power for cable will be more than surge power of overhead lines because the surge impedance of cable is lower than the impedance of the overhead lines. As a result, the surge capacitance, surge power of the cable is much larger than the surge power of the overhead transmission line. So now we have seen that the voltage and current waves are traveling and are composed of are superposition of the forward and the backward moving waves. Now, what will happen when the line is terminated? Till now, we have seen that the line is open circuit, and this type of the surge power, whatever input is given, it is also stored. Input is same as the stored now, but if there is termination of line, what are the different effects? So we have seen that voltage is sum of forward and backward. Current is also sum of forward and backward. And we also know that IF is equals to forward by ZC and IB is equals to minus backward by VB by ZC. And here we can say this is equals to VF by ZC minus VB by ZC. We can say I into ZC is equals to VF minus VB. And now if we sum these two equations, we get V plus I ZC is equals to 2VF. And so we can say that VF is equals to 1 by 2 V plus I ZC. Similarly, can write VB as V minus I ZC. Sorry. Okay. So you can say that V is equals to 2VF minus I ZC. Now, if we have a termination of line with resistance, then V will be I into R. I will be, because we know that V is also equal to 2VF minus IZC. I will be how much? We have this 2VF divided by R plus ZC. This is current. And V will become how much? Is multiplied by R. It will be 2R divided by R plus ZC into VF. So VF is equals to R plus ZC divided by 2R into V. Similarly, we can also find VB as R minus ZC by R plus ZC into V forward. And power transferred by the transmitted to the trans. So here we have this line and it is terminated with the resistance. So power which is transferred to the termination point by the forward wave will be Vf square by ZC, and our which is transmitted from the termination point by the backward wave will be V backward square by ZC. The power absorbed by resistance will be V square by R, which is also equals to V forward plus V backward whole square divided by R. Right. Because P forward minus P backward is 1 by ZC. V forward square minus V backward square, which is also 1 by ZC V forward minus V backward into V forward plus V backward. So which is equal to this is we know V by ZC into I ZC. So it comes out to be a VI. So PR comes out to V square by R. So this is also we have proven. Now the main thing which we saw in this week was the reflection and transmission, refraction and reflection coefficients. Because we have assumed that whenever there is a termination, a part goes is transmitted to the termination, so to the termination, and a part of the waveform is reflected back to the same line. So this also resistance. Similarly for inductance also we can just replace the resistance by inductance in that, and we'll find the value for the impedance also. So we got I is equals to 2R divided by R plus ZC into V forward. So here if termination is by impedance, we can say it is 2Z by Z plus ZC into VF. Similarly, V will become 2Z into Z plus ZC into VF. So now V is equals to tau VF, where tau is called as the refraction coefficient or transmission factor. So tau comes out to be 2Z divided by Z plus ZC, which is equals to V by VF. How much is transmitted? So here this is VF, out of which V, and we have V backward. So here we have transmission. So V is V forward plus V backward. So this current is here IF is in this direction, but IF backward is in this direction, opposite to VF. Okay. So similarly, so we have VB also. VB is equals to Z by ZC upon Z plus ZC into VF. So a part of forward it was transmitted, but a part of it also was reflected back. So the ratio of VP divided by VF, V by VF is transmitted, it is given by tau. But VB by VF is reflected, so it is given by rho. And this is equal to Z minus ZC divided by Z plus ZC. If it is represented by resistance, then it is, instead of Z, it is R. Instead of Z, it is R. Okay. So now, what is the value of tau? Here you can say tau is 2Z by Z plus ZC. If suppose Z is equals to ZC, then it becomes 2ZC by 2ZC, which is equals to 1. And if Z is 0, then it becomes 0. So tau will lie between 0 and 1, because impedance cannot be negative. So tau always lies between 0 and 1. And here if you see the reflection coefficient, then so that means if the open circuit, if it is open circuit, the termination is an open circuit, then there is infinite resistance impedance. It will be 2Z, Z we can take out common, it will 1 by ZC by Z. It will be 0, so it will be 2. Sorry. So tau is between 0 and 2. So when you can write it Z common, it will be 1 plus ZC by Z. When it is open circuit, that means Z is infinity. So this term becomes 0 and tau becomes 2. So because impedance can never be negative, so it will always lie between 0 and 2. Now let us see what happens with the reflection coefficient. Here if we take Z impedance as same as ZC, then it becomes 0. If we take impedance as now there are frequencies, and if it is 0 then it becomes -1. Z can be less than ZC, Z can be more than ZC, Z can be equal to ZC, and Z can be equal to 0. When Z is equals to 0, then it becomes -1. Rho is -1. Z equals to ZC, then it becomes 0. If Z is greater than 0, ZC, then it is greater than 0. If it is Z is less than ZC, then it is negative. Okay. If we have suppose this is, let's say this is Z. This is 0, this is ZC. Now we have three rays. One angle it is 0. When it is 0, it is -1. When it is ZC, then it becomes 0. In between this range, when it is less than ZC, greater than 0, then negative, and here it becomes positive. Okay. So now let us see what happens if ZC is less than 0. So we saw that if ZC is less than, sorry, Z is less than ZC, then that means it is negative. Reflection coefficient is negative. Negative means, because we are assuming that reflection will go like this. That means negative means VB is not like this, VB is like this, and it is adding to V forward. So when Z is less than ZC, what will happen to the voltage? Then V backward, which we have assumed like this, it will become opposite and it will become negative. And IB will become positive, because this I voltage, we know that IB is always minus VB by ZC. So if VB is reversed, VB becomes negative, then IB becomes positive. This is V, this is VF, and this is V back. So if Z is less than ZC, then what is happening? Rho is negative. Rho is negative. That means what was this rho? Rho was VB by VF is negative. That means VB is negative and I becomes positive. That means VB is like this and I is like this. Because I forward is also in this direction, I backward is also in the same direction, there will be increase in current. The reflected surge will consist of reduced voltage, because V forward is like this and V backward is like this. This is opposite to what we have assumed as convention. While the current is, both the current are in the same direction, so current is increased in the surge, in the reflected surge. Increased current we find in the reflected surge. This is very important. Similarly, we can also do this for the opposite. When Z is greater than ZC, then also the opposite thing will happen. That you can also try yourself. So just let me just tell you once again what is the convention and what are these reflection and transmission coefficients. So this we have considered as V forward. This is transmitted voltage, and this is the reflected the backward voltage profile voltage wave. So total this V is a sum of V forward and V backward. So if V backward becomes zero, then entire forward becomes is transmitted. So V divided by V forward is the tau transmission ratio, which is equals to that we have seen that it was equals to 2 ZC upon 2 Z upon Z plus ZC. 2Z divided by Z plus ZC. So when will this become 1? When will this become 1? Tau will become 1 when 2Z is equals to Z plus ZC. That means Z equals to ZC. So when characteristic impedance is line is terminated with characteristic impedance, then the entire forward voltage is transmitted. There is no backward voltage. So this is 2Z upon Z plus ZC. And then we also know the reflection wave is like this. V, which is Z minus ZC upon Z plus ZC. And this we already saw that there are different cases. Z less than ZC, Z greater than ZC, and Z less than ZC we saw here. What will happen? The V backward becomes negative, current becomes positive, so there is increased current in reflected surge and reduced voltage, and opposite will happen with the Z greater than ZC. So these two you should remember very well. These two formulas, and we'll find the most the excessive use of these two in the uh, numericals today. Okay, now let us see one more thing. So we saw that V by Vf is tau, right? And V backward by V forward is this, which is rho. Now we want to find out the relation between I backward and I forward. So this will be same as rho only. And we want to show that 1 plus rho is equals to tau. Tau is equals to 1 plus rho. That we want to show. How we can show that we know that V f is equals to V Z plus ZC by 2Z, and V backward is equals to Z plus ZC divided by Z minus. V backward is Z minus ZC upon Z plus ZC into V. So VB is equals to rho V that we know. And we also know that VB is minus ZC into IB. And this is rho into, so this should be, so this is plus, so this is rho into, this is ZC into I forward. So I backward upon I forward is equals to minus rho. And V backward by V forward is equals to rho. So there is a negative sign here. Okay. And this we already, we can, this is because of this. Now rho is equals to Z minus ZC upon Z plus ZC, right? So we can say rho plus 1 will be how much? 2Z upon Z plus ZC. And this we already know is equals to tau. So tau is equals to 1 plus rho. So if you know tau, we can directly find out rho. Tau is equals to 1 plus rho. So this is also an important relation which we should remember. Now let us see what will happen if there is open line termination and short line termination. short circuit. So we find that we will take certain question also. We'll see questions. Open. So what the last one was the termination of last one was the so here we saw tau is equals to 2z upon z plus zc and rho is equals to z minus zc upon z plus zc. So this is equals to vb divided by so v forward divided by sorry v divided by v forward and this is vb divided by v forward. Yes. So this is the same which we have to use when the line is terminated with a transformer. We have seen what happens to the resistance in the open circuit short circuit now. What will happen if the line is overhead line is terminated by transformer? So impact of high voltage of a surge on a transformer is also is similar to what happens when high frequency the distribution across each winding is modified due to the current between the transformer windings, between the turns of each winding and between each winding and the grounded iron core. The resultive capacitive voltage distribution can be represented in similar manner as one for a string of suspension insulator. Just we have did that. So the voltage of magnitude of surge voltage can be reduced by providing a short cable between overhead line and the transformer. So now we'll see what happens if there is a junction of two transmission lines. So there are let me keep this let this be like this only. For this formula we are going to use again and again. So here the ZC is already there. So ZC is we can replace it by ZC1. So we have one transmission line, then we have other transmission line. So this is ZC1, characteristic impedance of first transmission line. ZC2, the characteristic impedance of second transmission line. Let us assume that ZC1 is greater than ZC2. Characteristic impedance for first one is greater. So it is similar to a junction of overhead line and cable. The cable has such impedance. Characteristic impedance is less than the transmission line, overhead transmission line. So here you can say IF is VF divided by ZC1. So this is IF and IB is equals to minus VB divided by ZC1 and I which is transmitted is equals to VF divided by sorry not V divided by ZC2. Yeah, so this will be V which is transmitted. Similar to this. Similar to this. So V is transmitted and this is another region which is Z2. That's why here it is Z2, here it is ZC1, ZC1, ZC2 here. So we know that refracted plus transmitted is equals to forward plus backward. So transmitted wave is equals to forward plus backward. So V is equals to VF plus V forward. So same which we have already done. IF plus IB. So now we know IF we have written here. It is VF divided by ZC1. This is minus VB divided by ZC1. and I also here written V by ZC. So it becomes 1 by ZC2 is equals to, sorry, cannot move. You can say 2VF is equals to 1 plus ZC1 by ZC2 into V. So V divided by VF will become 2ZC2 divided by ZC1 plus ZC2. So same thing you can see here. Just make Z as ZC2 and ZC1, replace ZC by ZC1. So here it will become, rho will become ZC2 minus ZC1 divided by ZC2 plus ZC1. Okay. Yeah, so V forward will be V forward divided by ZC1. V backward will be V backward square by ZC1, and P will be V square by ZC2. This is V backward, we have V forward, and V is here transmitted. So transmitted is equal to forward plus backward. Now we'll see numericals. First, we'll take questions now. So let us see what is the first question. The first question is this: which of the following phenomena occurs upon the termination of a transmission line in an impedance smaller than its characteristic impedance? Yes, so it is here. It is talking about reflected voltage and current wave. So we have seen reflection coefficient is this VB by V forward, which is Z minus ZC upon Z plus ZC. Now it is said that termination occurs in a smaller impedance smaller than ZC. So it is Z is less than ZC here. That means rho becomes negative, right? If rho becomes negative, that means VB becomes negative. VB becomes negative. So earlier this was our VF, VB was this, but now if it becomes negative, then the voltage at the termination will reduce, and so IB is always V minus VB by ZC. It will become positive. So now what is happening? The reflected surge wave will have reduced voltage and increased current. See, this is the most important thing here. That is why we just derived it. So even if you remember the derivation, you will not remember the formula. You can directly start from the basic and derive it. So it's not very, it is not even time taking process. You can do it very quickly. Okay, so let us move next. So this is the first one. Next one is, yeah, so answer is small. So what will happen? Yeah, reflected wave. Yeah, so reflected, this is voltage. So the reflected voltage wave is negative and reflected current wave is positive. This is correct. Because VB comes out to be negative and IB is always opposite of VB, so it is positive. Backward wave. The reflected wave is negative. Reflected voltage and current is positive. So now this also we discussed. For a given voltage level, what is charge power in overhead lines? So this is P is V square by ZC. Now here it is asking us to compare the surge power of cable and surge power of overhead line. You can see this is line. Now, so for a given voltage level. So it will become inversely proportional to ZC. So we know one thing that ZC of cable is less than ZC of overhead lines. So now because surge power is inversely proportional to ZC. So if ZC for cable is less, then the surge power for cable will be more. So surge power in overhead line is smaller than in cable due to greater surge impedance in overhead line. So this is correct, right? The surge impedance of cable is less than surge impedance of overhead lines. As a result, the power surge power in cable is more than surge power in overhead lines. Yeah. So now let us move to the next question. Next question is this. Next is the refraction coefficient of voltage and current at the load end of a short circuited line. Yes, this also we have already seen. This is also easy question what we have already discussed. It is refraction coefficient or the transmission coefficient. The transmission coefficient is this tau, which is 2z upon z plus zc. So for a short circuit line, what is z? Z is 0. It becomes 0. Okay. So this was transmission coefficient for voltage because we said this V is V by V. This is tau is equals to 0. But now we also want to calculate I divided by I. So I was how much? V by Z. And IF is V by ZC. VF by ZC. So this is how much? ZC upon Z into tau. So this is ZC by Z into 2Z upon Z plus ZC. This is cancelled. So this becomes 2ZC upon Z plus ZC. Now it is saying Z is 0. That means I by IF becomes 2. ZC is 0. And Z is also, sorry, Z is 0. So it becomes 2ZC by ZC, which is equals to 2. So what is the correct answer here? So correct answer is A here, right? This is easy, right? I can just, I would like to, I will explain it again. Uh, yes, in the previous slide, we discussed that transmission coefficient or the refraction coefficient for voltage we derived. That was 2z upon z plus zc. Because z here is 0, so it becomes 0. But now similarly, we can also find the transmission or refraction coefficient for the current, and this will be equals to V divided by Z, and this will be VF divided by ZC, and V by VF we already know, and this is multiplied by ZC by Z. Z. And V by VF is 2Z upon Z plus ZC. This is multiplied by ZC by Z. So this is cancelled. This becomes 2ZC upon Z plus ZC. Now, so this is unit current tau current reflection coefficient. This is voltage reflection coefficient is 0. It becomes 2ZC upon Z plus ZC, which is equals to 2ZC upon ZC, which is 2 because Z here is 0. Right. Now let us see the next question. The next question is this. So what we have a long transmission line which has line impedance is given as 0.452 millihenry per kilometer, and assume that the receiving end is open circuit, and distance traveled by a 110 kV surge voltage wave. This is in 10 microseconds is 1.5 kilometer. So this is a distance travel in 10 microseconds by 110 kV. So we have to determine the surge power in megawatt. We have to determine what is the surge power. So what do we need to find here? Yeah. So we know the velocity, the surge velocity in formula for surge velocity. And what is surge power? Surge power is V square by ZC, and ZC is root L by C. So now we have L, but we don't have C. So this we have to find out. For this we need C. So C we need to find out first by using this surge velocity principle or formula. So, and we know that surge velocity is V kilometers per second. So surge velocity we know that V kilometers per second, and which is V we know that it is 1 by root LC in kilometers per second. So, V into time will be equals to distance, right? So V is 1 by root LC is equals to distance divided by time. So distance is how much? 1.5 kilometers divided by time is how much? 10 microseconds. So 1 by root LC is equals to 1.5 into 10 to the power 5. And so LC is equals to 1 divided by 1.5 into 10 to the power 5 root. How much is this? Let us calculate. Into 10 to the power 5 root total answer is 387. And root inverse. This comes out to be 2.582 into 10 to the power minus 3. And we need to find out C. So C will be divided by L. So C will be divided by L is how much? 0.452 millihenry. Very some. At info square we need to do, sorry. It will be LC, and C will be divided by 1 by L. This we have to do. 2.5 into 10 star 5 square inverse divided by L. 0.452 plus L square minus 3. It comes out to be, how much is the answer? You can calculate this. Hmm. Is from here only. It was 1.5 into 10 square 5. And you need to do square. Square. So capacitance comes out to 0.1046 microfarad per kilometer. And if we substitute this in this, so we find out L by root C 0.452 into 10 divided by, this comes out to be 65.74 ohms. So this will the answer will be 1, or will come out to be this between this one. It will be how much? Around something 186 megawatts. Yes, so main thing here was just to first calculate because we know that velocity is 1 by root LC. So you can easily find out C from here. Then once C is found out, you can know you can find out ZC, and once ZC is known, you can also find out the surge power. So now let us go to the next question. The next question is uh, I will just speak this to insert a new slide. Yes. The next question is this. The next question is this. Yes. 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 The next question is there is a transmission line which is having a surge impedance of 100 ohm and is terminated by a impedance of 155 ohm. If the magnitude of forward traveling voltage and current, the VF, is given as 4.8 kilovolts and forward current is also given as 13.7 ampere, then determine the voltage at the end of the line. So we want to know the voltage at the end of the line. So voltage transmitted is below. We want to find out V forward plus V backward. So this is the information which is given to us. So how we can do that? Because we already know, right? So we know ZC, so this is ZC, and we know that reflection coefficient is, so, so we can find out the transmission coefficient instead tau, which is known as 2z by z plus zc, and this will be equals to 2 into 155 by z plus zc, which is 255. So tau comes out to be 255. So it is 1.22. Tau is 1.22, right? So, and we know that tau is equals to V by Vf, and we want to know V, so V will be 1.22 times Vf. So it will be multiplied by 4.8. So it comes out to be 5.8. It is 5.8 kV. Right? So it was very easy question. So this was the only thing which was to find out the voltage at the end of the line. So yeah, 5.8 volts, 8 kV. Very easy question. Now again, so let me insert one more slide. Yeah. So next question is transmission line having determine the current in the ampere flowing through the instrument. Yeah, it's the same question. Same question here. We want to find out. Yeah, we want to find out what is the current in amperes. We want to find current which is flowing through the resistor in amps. So I is equals to IP plus IF, and this is also, so we also know that I divided by I forward is equals to 2 ZC by Z plus ZC, right? So this will be equals to 2 ZC is how much, 100 divided by Z plus ZC 255 into 5. So 200 divided by 255. So this becomes 0.784. So I becomes 0.784 multiplied by the 30.7. It becomes 24.08 amperes. So it comes, it is in which range? Have I made a mistake here? Forward voltage and current waveform. Uh, just a minute. So, yeah, is I can directly write as V divided by R. So it will be 5.8 V divided by 155. How much is this? So this is 37.42 amperes. This is correct. We need to find out the current in the amperes flowing through the resistor in amp. This will be current flowing through the resistor V divided by R. So here we can do it as current will be into VR divided by R divided by this. I is equals to V by Z, right? So that only we have done. Directly we can calculate. So I was thinking I divided by IS is also is not a rule. It's V divided by Z and this is VS divided by Z. ZC. It becomes V by VF into ZC by is equal to, yeah, this is also correct, right? V by VF is 1.22 into ZC is 150 into 100 divided by Z. So this will be current reflection coefficient. The current reflection coefficient will be around 0.7. So here it is simple V by R you can do. Next, let us go into the next question now. The next question is an overhead line with the surge impedance of ZC is 275 ohm is connected to a transformer by a short length of cable. Z cable of 1.102 ohms. If the rectangular surge wave of 115 kilovolt travels along the line towards the cable, this is V forward. Then the voltage of the wave traveling from the junction of the overhead line to the cable V we want to find out to the transformer. Here we have transformer. This is cable and this is overhead line. If we want to find out this voltage V, so we know that tau is equals to 2 Z by Z plus ZC Z cap 2 into 102 divided by 275 plus 102. Yeah, so this is how much is this? 275 plus 102. So this is around 0.54, and so V divided by V forward is equals to tau, which is 0.54. So V will be 62.23. Yeah. So answer C is correct. Yeah. Now, same question. Voltage of wave traveling from the junction of overhead line to the cable towards the transformer. So the voltage of wave traveling. Yeah, this is the. What voltage is reflected back into the line? So this is transmitted. We want to find reflected. So we know that rho is Z minus ZC upon Z plus ZC. And also we saw one thing, another relationship we found, right? Where is that? Now I've missed that. Okay, leave it. You can directly see here. It is Z minus ZC upon Z plus ZC. So this is 102 minus 275 divided by Z plus ZC. 275 plus ZC is 102. So this is minus 0.46. So this is V backward divided by V forward. Minus 0.46. So V backward is multiplied by 115. This is minus 52.77. The answer is correct. So this is minus 52.77. A simple application of formulas for the reflection and transmission coefficients. Use it and you can directly find out all the values. Voltage as well as current. Let us see the next question. Next question is, in a lossless transmission line of length, first it is lossless and then length is 40 centimeter. It's small, 25 microhenry per meter is L, C is 75 picofarad per meter, and frequency is 50 megahertz. So it is for a communication line. Its electrical path length is. We want to find out the electrical path length. So electrical path length is beta into L radian, and velocity we know velocity is v, which is 1 by root LC. We can find out this by using the L and C values, and then lambda is v divided by f. So beta L comes out to be 2 pi by lambda into L. So length we know 40 centimeters. It will be 2 pi f by lambda v by f v into L. This is 2 pi. Frequency is given 50 megahertz. V we have to calculate. L is 40 into 10 to the minus 2. This is 1 by root 25 into 10 to the minus 6 Henry. 75 10 to the minus 12 farad. How much is this V first we have to calculate? This is 0.2309 into 10 to the power 8 meter per second. So this we have to substitute here and find out what is beta. So we realize 25.5 2 to 5 50 into 6. So this comes out to be 5.44 meters. So the electrical path length is beta into L radians. Again, you can summarize, and this is equals to 2 pi by lambda, and this is L, and lambda we know that it is V by F, so this is V into F into L, and we also know that it is 1 by root LC, so it is 2 pi F by root LC. Beta L is this, or we can say this is beta L. Or we can say beta is equals to 2 pi F root LC. So this will be in per meter, radian per meter. This will be in radians per meter. But if you want beta L, then it will be 2 pi FL root LC in radians. So this is also done. So let us see, move to the next question. So here the question was that we have a lossless transmission line with a length of 40 centimeter with L 25 microhenry per meter, capacitance is 75 picofarad per meter, and frequency is 50 megahertz. By frequency and this length only, we can know that this is not a power transmission line. It is a communication transmission line. And the question was to find out what is the electrical path length. Electrical path length is this, beta L in radians. This is the electrical path length. And this we can easily find out using this one. Because beta is the wavelength, sorry, beta is this 2 pi by lambda, lambda is wavelength, and lambda is wavelength is equals to v by f, speed, velocity by frequency. Frequency we know, and velocity is 1 by root LC, so we can substitute it here. So beta L comes out to 2 pi FL root LC. Okay, now let me add one more slide. Yes. So we'll see one more question. So the next question is, there is one overhead transmission line. It is connected to a terminal apparatus through a length of single phase cable. So when we have a transmission line junction, then we have a cable here, And here is some apparatus. So this is a single phase cable. And the characteristics impedances are 360 ohm and 120 ohm. A traveling wave of 165 kilovolts magnetic originates in overhead line. So this is given as the VA and travels toward the junction with the cable. We determine the energy transmitted in the cable during a period of 5.5 microseconds after the arrival of the wave at the junction. So we want to find out the energy transmitted. The question is to find out the energy transmitted into the cable during a period of 5.5 microseconds after the arrival of the wave at the junction. Okay, so this is the question. The energy will be P into time. So we can calculate the power transmitted into the cable from the junction. The power transmitted will be how much? V square by Z cable. Now we want to find out what is V. V is V backward plus V forward. And we also know that V by Vf is the transmission coefficient, which is 2Z by Zc, which we know Z is 120 divided by 360 plus 120, 420. So it is 1 by 4, so it is half, 0.5. So V is half of 165, 165 by 2. It becomes 82.5 kilovolt. Okay. So now we can find out what is power here. We know voltage is 82.5 kilovolt divided by Z cable is how much? 120. So this is the power. How much is this? Divided by 220. This comes out to be 0.567 megawatt into 10 to the minus 6. Yeah, so it is correct. 0.567 megawatts. So what will be energy? Energy will be into time. It will be multiplied by 5.5 microsecond. It comes out to be 2.5. So this is transmitted voltage, and transmitted current will be V divided by Z cable, which is 82.5 divided by 120. How much is this? This is 0.6875 kilo amperes. Now we can find out power, or directly we can find out energy transferred is ET into IT into time, which is equals to 82.5 into 0.6875 into 5.5 into 10 to the power minus 6 into 10 to the power 6, because these two are in kiloamps. How much is this? 82, 82.5 into 10 to the power 6. That's 1.45. So this comes out to be 311.95 joules. It should also come by using V square by ZC, Z cable. There is some mistake which I have made. 82.5 times power 3 divided by Z cube. How much is this? 82.5 into 10 power 3 square divided by 120. Yeah, correct. I made a mistake. So it comes out to be 56.718 megawatts. Now this is power. Let me do it again. Let me insert one more page here. Yeah. So we found V transmitted to be zero point 0.5 times V forward, which is 82.5 kilovolts. Z cable is given as 120 ohms. So we can know that power which is transmitted in the cable is V square by Z cable, where V is 82.5 kilovolts. That is V square divided by cable is 120. So this comes out to be this comes out to be 56 watts. So now we want to find out how much energy is transmitted over a duration of 5.5 microseconds. Then it becomes C cap into T, which is time duration. It is 56 10 to the power 6 into 5.5 microseconds. So this comes out to be same. Should come same. I was making some mistakes. There was one. I was getting 3.11, so there was some calculation. Now this is correct. So this is 311.95 joules. So let us do one more problem, then we will wind up. So next problem is this. Yes. So we'll take the same problem which is given in the lecture notes also. Maybe if you have not gone through it, you can refer this. So here the question is an overhead transmission line is connected in series with an underground cable. Again, so first is the transmission line, then we have a cable. So characteristic impedance of transmission line is 400 ohm, and this is 40 ohm. So Z is less than ZC here, and we have already seen that Z is reflection coefficient is this. So it is, since Z is less than ZC, it is negative. So VB becomes negative. And because V becomes negative, so what happens? Voltage reduces. That is why we use, if we want to reduce the voltage, can we use short cable? So in forward traveling, voltage is given as 200 kilovolts. I'm traveling towards the junction. So we need to determine the magnitude of the forward current. First, we determine the forward current magnitude. So we know that. So forward current magnitude is very easy because we already know this forward voltage and we also know the impedance of the transmission lines. Forward impedance voltage will be IF, EF divided by simply its impedance. It will be 200 kilo ohms, kilovolt divided by 400 ohms. So it will be 500 amps. The next thing is we have to find out the reflection coefficient and refraction coefficient for both voltage and current. So let us first of all find out the reflection coefficient for voltage. So refraction coefficient for voltage, which is also the transmission coefficient, both same. It is V divided by Vf. And V already, and this is equals to 2Z divided by Z plus ZC. So this is 2 into Z. Z is how much? 40. This is divided by 440. 2 into 40 divided by 440. So this is 0.182. So we can know so refraction coefficient is 0.1818 or 0.182, and so transmission this reflection coefficient will be Z minus ZC upon Z plus ZC. Or we also know that tau V is equals to 1 plus rho V. So we can calculate the rho V as reflection coefficient for voltage as tau V minus 1, which is 0.1818 minus 1. So it is minus 0.8181. Okay. Similarly, we can also find out the reflection or transmission coefficient for current, which is equal to I divided by IF. Yes, and because this will be 2ZC divided by Z plus ZC. This is 2 into ZC, how much? ZC is 400 divided by Z plus ZC is 440. So this is 1.818. Uh, 1.818. This implies current is 1.818 times of forward current. IF. How much? It is 500. So how much it will be? 500 into 1.818. So it is 9099. Last time somewhere I have made a mistake, right? Here we wanted to find out the forward current. Here V by R. So here we found tau as 1.22 and forward current, this was ZC, this was Z. Yeah, so this is done. Now what we can do is we can find out. We have found out the transmission coefficients. Now the reflection coefficient for current is IB divided by IF. And this is minus VB by ZC divided by I. IF is VF by ZC. So this becomes how much? Minus rho V. So the rho V was how much? Rho was this, so rho I comes out to be 0.8181 into I forward. This implies I backward is equals to 0.8181 I forward. I forward is 500. 0.8181 into 500, 409. So I backward is 409 amperes. So because here Z is less than ZC, VB becomes negative and IB becomes positive. So reflected voltage wave has a increased current, and which is equals to 409 plus 909 ampere. No, not this. Forward is 500. So it is 909. Okay, so what was left now? Mm, the plot will be something like this. So it is I. It will be like this. So this we calculated. This was I forward, which was how much? I forward was how much? I forward was 500 ampere. So this is 500 and this is 909. So this was 409 amperes. I backward. But the voltage will be reduced. So V forward was how much? V forward was 200 kV. This was 200 kV. But then it is reduced. V backward how much? V backward is uh, oh, we have not calculated V backward. Reflection coefficient we have calculated, but voltage we didn't calculate. So this is equals to VB by VF. So VB is minus 0.818, 200 into 0.8181, 163.62 minus. So this is 163.62. So 1 plus 200. So overall, this will come out to be 36.38. So this will be V. So this is the V which is transmitted. So V is transmitted. Transmission coefficient is only 0.182 into, so it is same as 36.4. So this voltage is transmitted. Small because Z is less than ZC. If Z is greater than ZC, then this voltage will be more. Current will reduce. Transmitted current will reduce, but the voltage will increase. Okay, so we have discussed all the questions for today. Let us stop here. We'll meet same time uh, next next week.